View this talk on the entropy and the Ricci process.
All right, so let's recall some basic information of last time. So we have two normalized Ricci flows. A is the final case. B is the general type minimal. So we have the equation derivative of g is negative Ricci plus g, and the negative Ricci minus g. And on the potential level, so it's use derivative is log omega t to n over omega n plus u, and partial t partial u equals log omega n to the capital omega minus u. We say that the volume behavior, this is a constant, and this is converge or approaching to. So in many cases, these two pictures dual to each other. This minimal genotype has two, can be understood in this way. You consider the canonical line bundle Km. So here the genotype minimal means Km n not equal to 0, and Km is nef, numerically effective. That's the meaning of minimal. Genotype is Km to n not 0. So basically, I think this genotype comes from this way. Because in the complex dimension 1, you have the classification of the surface. There are the sphere, the torus, and all high genus part, high genus surface. The high genus corresponds to the genotype. That's the reason why it's genotype means it's Km greater or equal to 0. Genotype is Km not 0. Km greater or equal to means nef, minimal. Okay, so now we compare. I recall some estimates. So of type A, we have the estimates by entropy method of Perman. Perman shows that the scalar curvature plus diameter bounded, kappa non-collapsing. And then we have this kappa non-inflation. Okay, this together means this volume of BXR over R to the 2. And this volume ratio function is bounded from below and bounded from above. Right. So then you have the convergence. So these are basic estimates. Then you have the convergence. Now after the convergence, you have the uniqueness of the limit. I forgot to mention this at the end of last time, but it's known that after you obtain the convergence, the uniqueness of the limit is known. I mean, so so this convergence means for TI.
No condition. It's in the chain class. You start with initial class.
Yeah. The positive first chain class case.
So
this is A. This is C1M positive. And by the uniqueness, I mean this M hat does not depend on the Ti. So for each Ti converged to infinity, by taking subsequence you obtain a limit. But this, in general, it could depend on the choice of Ti. By uniqueness of the limit, we say this does not depend on Ti.
Just underlying manifold.
This complex as a complex variety, it does not depend on Ti. This uses some rigidity of complex analysis. We put this. We use power theory estimate to put everything into a big but a fixed dimensional CPN. Then in the CPN you can apply complex analysis, reduce this to an algebra problem. So then there is a, I mean, this is reduced to.
Metric.
After you decide the uniqueness of the complex variety, then the metric is also rigid. But you have to deal with the variety first, the complex structure first. And then G infinity as a metric is also fixed. So this convergence in the C hat infinity Chigger Gromov sense. So this unique means isometry. If you have a 2 M hat G infinity, let's say X hat H infinity, then they are isometric. The step is first to show as a complex variety, they are isomorphic. Then for each complex variety, if it admits a Ricci-Thornton metric, there is a uniqueness theorem by Tian Zhu. So the metric is also unique. Okay. So that's about the final case. Then we consider the case B, the C1 of M less or equal to 0, and okay. So by different method, it's known that scalar curvature is bounded. So this is by Zhou Zhang, 2007. Scalar curvature is bounded. This is by maximum principle. But how about the diameter? It's not clear. So then of course it's not clear where do we have this non-collapsing and the kappa non-inflation. So this is also unknown. But of course all these are known in dimension 2 or dimension 3. So this is known in dimension less or equal to 3 by the work of Ben mentioned this yesterday. I think this is almost the same time. So in dimension 2 or 3, it's known that the diameter is bounded, and you have this non-collapsing. And I mean, after non-collapsing to obtain this is not very hard. Then in high dimension, this is not known. And then you compare this convergence. It's not clear if we have this Chigger-Gromov convergence. We do not even know this Gromov-Hausdorff convergence. In the final case, we have the Gromov-Hausdorff convergence because there is a volume doubling, right? But now this volume doubling is not known. We do not have non-collapsing, so it's not clear whether this sequence converges to a limited metric space.
Assuming the C1n not equal to 0, right?
No, the non-collapsing case. Yeah. If it collapses, it's much more complicated. So then, how about the convergence? In this topology, it's not known. But as mentioned yesterday, so you know this convergence is omega t converge to omega singular Kähler instant. It's in the smooth topology away from an exceptional set. So this is done by complex Morin-Ampère equation method. So this is known, but not in the Gromov-Hausdorff topology. Away from the exceptional set, you have smooth convergence. But the information around the singular set was lost. And then you also have, you consider this uniqueness problem. Well, of course, you cannot say too much now, because you even do not know if the limit exists. But the point is, suppose the limit exists, then it must be unique, because in the convergence of the current away from the exception set, this omega ke is unique. And it is conjectured that this M canonical model omega ke, so this is the metric completion of the Kähler-Einstein metric on M without B. So this is a metric completion. So it is conjectured that this is so Gromov-Hausdorff.
Case that dimensions less than equal to 3, do you know that your diamond is bounded?
It is known. I forgot to mention that. So this one, as a completion of the omega ke on this part, has a bounded diameter. So the diameter of where do I say? So I should put it here. So the diameter of this is a canonical model of M. So this is bounded, let's say, by L. So this is a result of Jian Song. Basically, that's you solve the Morin-Ampère equation, and you estimate the behavior around the singular set. So he obtained this bound. Now, so there are several things which is not clear, but you go through the proof, you'll find that there is a key estimate. So after you solve that estimate, then all the others will follow. That's the carbon non-collapsing. So why this carbon non-collapsing causes trouble? Because you know this M omega Ti converge C infinity local x away from B to some M canonical omega Ke. Now it's so it is possible that it converges in this way. There is a very long, but very tiny stuff. Finally, it converges to this. So this is the omega Ke part, right? It's a metric completion. But when this part converges, it is possible that there is a low dimensional infinity length line there. Right? So this is it. You have to rule out such a thing. So that's the key difficulty. I call this as a cusp. in order to show the convergence in the Gromov-Hausdorff topology, you have to rule out the cusp. So, suppose you can show this kappa non-collapsing, then you can rule out the cusp. The thing is this. Suppose kappa non-collapsing is low. Then cusp does not appear. Because, this Ricci flow, type B, it converges to the volume behavior. The volume is almost constant in the infinity. And all the volume are captured by the regular part. There is no volume on the singular part. So suppose you have a diameter infinity along the flow. Say I can choose a point very far away from the regular part. Then I choose a geodetic ball. Then its volume will converge. Let's say this is B. The volume of B will converge to 0, right? But this B, now I choose a point, a base point x0 here. I can say that the distance from x0 to B is about 2L. So by Thom's estimate, the regular part has diameter bounded by L. So I can choose a point whose distance to the regular part base point is 2L. So then by the current convergence, this volume will converge to 0, right? But if you know kappa non-collapsing, you will be a contradiction. So this will violate the kappa non-collapsing. So using this argument, by refining this argument, you will see that suppose you have this kappa non-collapsing proved, then this convergence actually will behave in the Gromov-Hausdorff topology. Okay. That's a key difficulty. So this will be true if kappa non-collapsing. And also, basically, this will if you can show the kappa non-collapsing, it will solve the major difficulty, and it will imply the other estimates. Diameter bound and diameter must be bounded, because if diameter is very large, then you can always choose such a B. And actually, you can show the diameter must be the conversion to the diameter of omega ke. So now, we call this Hamilton's program to solve the Poincare conjecture. The key difficulty is kappa non-collapsing. Right. But that kappa non-collapsing is for a short time singularity. This is for the Ricci flow, but you will see this is the kappa non-collapsing at the time infinity. So somehow you need to develop a non-collapsing estimate. We need kappa non-collapsing estimate for a Ricci flow. Long time singularity. But in general, it's impossible. So that will be too hard. For a general Ricci flow with a long time, this is almost impossible. But the point is, for this Ricci flow, the Ricci flow of this type of B, you can obtain much more information from the estimate of this. So actually from the complex Moran-Pig equation. So now you can again compare the picture of A and B. I have drawn such a graph. So this is A. So on one hand side you have the Chick coding theory, which deal with the metric structure of the space of Ricci equals 0, greater equal 0 actually. And the other side is Hamilton Perman's Ricci flow. So Perman has based on the work of Hamilton, has developed a space-time structure of the Ricci flow in terms of reduced distance. If you use the perspective of the reduced distance, the space-time of the Ricci flow can be regarded as Ricci flat if you reduce the volume comparison geometry. So then what do we do for the type A Ricci flow? What do we generalize to singular Ricci flat space. Right. So we generalize Chick coding theory. Then I can combine the Chick coding theory with the Ricci flow theory to study the final Ricci flow. But here things are different. Because all the thing I can do for the final case is based on the carbon non-collapsing condition. That was obtained by Perman. But here, in the type B Ricci flow, you do not have carbon non-collapsing. So the difficulty is the carbon non-collapsing. You have to solve this carbon non-collapsing directly. But it's not clear how to solve this directly. What do we need? So for this is for the part A. So this is for the flow B. What do we need is to generalize the Ricci flow theory of Perman. So the Perman's entropy method is developed to study the short time singularity. So that's why he have a carbon non-collapsing here. But this is a long time singularity. So the carbon non-collapsing does not work directly. So we have to figure out a way to show this non-collapsing directly from the entropy. Okay, so now let's go over the basic thing why the carbon non-collapsing holds for the final Ricci flow, and cannot be obtained directly by Perman's method.
It's the unnormalized one that's finite time to go up, right?
Yes,
the
yes.
Other one is
It's a long time. Yeah, that's the difficulty. You have to deal with why is finite time singularity, why is long time singularity. So now we need to develop a non-collapsing for the long time singularity. So it does not work directly. So let's see this. That's one of the methods to observe. The other thing you can see is I recall the entropy. So for a manifold MG, the Perman's entropy can be defined in this way. So W M G F equals so this is the result tau R plus gradient F square. I use M, so this is the real dimension. And then, of course, there is a normalization condition. So this is then we consider what is mu functional. So it's the infimum, taking the infimum of all the f satisfying the integral of pi tau negative. So this is the mu functional. And then you define the nu functional. So the infimum of all this mu and g tau greater than 0. So that's the definition of a Perelman's mu function. Then Perelman's deep observation shows that along the Ricci flow, you consider this new functional of a MGT. So this actually is non-negative. Actually, it shows that this ddt of mu of m gt capital T minus T, this is increasing. So now let's apply this observation to study the local collapsing of short-time singularity. So now I have I have a Ricci flow. This is Ricci flow space time. This is T. This is M. Now this is T equals 1. This is T equals 0. Now I suppose the singular time is around the T equals 1. Say. Okay, so then according to Perelman, we know that the mu functional of M G1. Let's say this is singular time. Now at the time 1 minus tau. Say at this time, I choose a ball. I call this the best point as y0. So this ball has the this is a general t. Let tau to be 1 minus t. So this is the radius square root 1 minus t. So this is mu functional at the t of the tau, which is 1 minus t, or greater or equal to but for initial manifold, this is a bounded number. For initial manifold, then you have a mu function bounded from below. Then I choose the test function like like this function. Let's say eta of the distance y0. So eta is some function like this. So it's 1 here. So 1 here. 0.5 smooth. Then you obtain this W functional of MT 1 minus T of eta, maybe some log of eta. So this will be greater or equal to negative C. Because it's greater or equal to this and negative. And this will imply the carbon non-collapsing. So that's the proof. The mu function of the lower bound implies the non-collapsing. Of course, you can apply this new function directly if you want. If you like use this new function directly, you will see that the new functional of mgt of greater equals the new functional of mg0. So suppose the initial scalar coefficient greater than 0, then this will be greater than negative infinity. Then from here you obtain directly you have the non-collapsing. Okay, so if I use this explanation, you see that where is the difficulty now?
Yeah, but this is designed exactly for finite times.
Right. That's what design exactly for the finite times.
So you might want to use the other.
What I would say is if scalar coefficient if scalar coefficient is less than 0, this new function is negative infinity maybe. So you cannot use this directly. But you can still use this part, but then you have some extra term that is time t will appear in the extra term, but t goes to infinity. So that will destroy the estimate.
What about the other one, the constraint by the
You mean the forward one?
There's a dual one.
Yeah, there's a dual one, forward one. Yeah. So discovered by President Lee and Feldman. I tried that, but it didn't work directly. Yeah, but that doesn't work directly. So, okay, so this is the difficulty. Why you cannot apply this directly to obtain the carbon non-collapsing. But then I turned to the reduced geodesic and reduced volume picture. I found that it's very close to the solution. So what is the reduced picture? Reduced distance picture. Maybe I can keep this. So you have a Ricci flow. Again, I use horizontal direction as a manifold direction. I choose the best point x0 here. And I assume there is a space time such that the remaining curvature is uniformly bounded in this space time. Okay. So in ball of GT of x01 for every t in 01. Okay. So remaining curve is uniform bounded. Then I choose a point far away. I choose a point not located in this bounded geometry part. Very far away. The distance maybe capital A large. Okay. Now the thing is, can you talk something about the local behavior of this point y01? Y0 very far away from x0. This is x0. So Perman has a theorem in chapter 8 of his foundational paper. He said that you can use the reduced volume picture. So suppose the y01 say has a ball or radius r in BG1 or y0r. You have this remaining curvature bounded by r to the -2, and t is from 1 or 1 minus r squared. Suppose you have a curvature bound here. Then you can consider the reduced volume best at the point y01. So let's recall what is the reduced volume. So reduced volume defined by Perman means this integral of 4 pi tau to the power negative m equals 2e to the negative l y0, 1 to x, say t dv. So this is the reduced volume. Reduced volume best at the point y0, 1, and with the scale tau, where tau equals to 1 minus t. Okay, so for each t, there is a reduced volume. So reduced volume depends on t. Fixed base point depends on t. Right. This tau equals 1 minus t looks like radius square. They have the same scaling factor. So using this reduced volume picture, Perelman shows that you consider the reduced volume. But if you consider reduced volume at a tau equals 1, and you consider the reduced volume of the radius, let's say r square. So I choose this small tau reduced volume, and this large tau equals to what? Reduced volume. There is a natural motonicity, right? There is not such a motonicity, but because around the y0 you have a curvature bound, so this reduced volume actually gives you the information of the volume ratio. So this gives you, so this is almost the volume ratio. Almost the volume ratio of the ball of radius r naught. But how about this one? It will have a lower bound because it, by definition, is the integral of e to the negative l. L is a reduced distance. Because reduced distance almost the Lagrangian, I define this morning divided by 2 times square root of tau. So here is almost a Lagrangian. But then you can see, Perelman shows that for every, you can choose a geodesic y0 to x0 around such that the L of y0, 1, x0 of, say, delta, this is bounded by C. Okay, so that gives you a bound of the reduced distance everywhere is bounded from above by C. So this will be bounded from below by 1 over C. Okay, so that means this will be bounded from below by 1 over CC, some universal constant, times the volume of Bx0, 1 at G0. So that means if you have a non-collapsing here, you have a non-collapsing here. There is a propagation of the non-collapsing. So this is Perelman's theorem in chapter 8 of his paper, right? But so I try to use this theorem, but the difficulty is also clear. So y0, 1, this is when I try to develop the carbon non-collapsing. The really difficult part is the part around the singularity, right? So you cannot have this strong condition, curvature bounded around a neighborhood. If I know this, I can use the Marhapi equation method directly to solve the problem. So this is not known. So this condition is too strong. It's not available. Right. But I thought for a long time. I think the key is in the Lee-Yao-Hanaka inequality. So from the Lee-Yao-Hanaka inequality, we can re-understand the structure theory of Perelman. Then I can remove this condition. So Perelman requires this remaining curvature to be bounded from above in a space-time neighborhood. I can.
We
get to scalar curvature bounded by R2 negative 2. And we do not need the space time information at the time t equals 1. In interval BG1 or 0. Yeah. So if you have this, of course, I think this is done. Because scalar curvature bounded is known. Right. At the time t equals 1, this non-collapsing, of course, depends on distance to x0.
That you were comparing the original argument, you don't look, but you don't look.
Yeah, so I think, I want this, and I can show this. So that's my point. So I think this is the difficulty. So using this comparison geometry picture, it indicates that it's almost true for the type B characteristic flow. But the difficulty here is Perman's original argument does not work. It requires two strong conditions. But then the thing is, how do you overcome this difficulty? By removing this condition? So, so how long time do I have? 10 minutes? Okay. So I will try to finish this in 10 minutes. Of course, I will skip some.
How do you pass for finite time?
Yeah, that's a very good question, actually. So actually, every time you can rescale the flow, so that so for every okay, so let's explain how does this work. So we in general do not know this long time non-collapsing, but we know there are some points with a good neighborhood which is always cover non-collapsing. Because let Ti tends to infinity, I choose Ti minus 1 as the best time. Then you have a parabolic rescaling, so that is still a finite time singularity. So Ti, you compare Ti times size with Ti minus 1 times size, then this parabolic rescaling is almost trivial. I normalize it at Ti minus 1. Then I study Ti. This normalization, the error caused by the normalization is control, can be controlled. Okay, so then how do I show this? So I record this. So we need to really understand this function. So actually, this function, this is the integral tau. Okay, this is the W functional. Let's just call W. I rewrite W as this. This was well known. Tau R plus 4 gradient phi squared plus phi minus let's see. There is a log tau. There is a phi. Yes, thanks. Let's say minus phi log phi. Okay. So here you choose phi square equals. Right. So this is well known. Then you obtain. So I found this is more natural to consider the W function in the phi. Then the thing is, I think I need to erase this part. I can localize this functional on a compact domain. Then I define this mu functional of omega g equals to the infimum of all the phi square integral in omega equals 1 phi. And then this is I replace the support set from M to omega. Then the good thing is, it's known in the literature of logarithms of level inequality that the minimizer always exists. And then you have this Euler-Lagrangian equation. Okay, so then the interesting thing arises. So what I do is I do not use the reducer geodesic. Instead, I want to compare x0 and y0 neighborhood. Right. So around here, I choose a ball, which is I call it omega, is by0r. I start from a phi, which is the mu functional of g of some tau 1 omega. Yeah. I consider this phi is an eigenfunction. So of course, in omega, the integral of phi square will be 1. Okay, so I let u to be phi square. And then I solve the equation square star u equals 0. Okay, so the good thing is that this u will be greater or equal to 4 pi tau negative half dimension e to the negative L. So u has a lower bound here, right? So u has bounded from uniformly bounded from below around the x0. Okay, but what is the advantage? I choose phi as an eigenfunction here. So this part is technically not that easy, but the intuition can be explained very clearly. So I start from this u, which is an eigenfunction, right? And the eigenfunction is good because it satisfies this Euler-Lagrangian equation. Right. Okay, so now we observe, I move this part to the left. I consider so how do I say? I define a function. I define a function which is tau m plus 1 minus t. Twice the Laplacian f minus gradient f square plus r. Okay, so let's see. Suppose this is tau, then this is a function defined by Perman. If this is tau, then you multiply this by u. This is a function defined by Perman, right? Then Perman showed that the square star of v is negative 2 tau times ij plus fij minus gij over 2 tau square less than 0. Okay, but currently we formally you can still do the calculation here, but you start from something which is more weird. Perman's starting point, you start from a delta function, right? So then this equals 0, and you obtain V less or equal to 0. Right.
Also minus there, or that is the
Which is minus?
where the last term is minus over 2,000.
Minus Jij over 2 tau. Oh, sorry, I have a U here. Yeah. Okay, so basically the interesting thing is here is not exactly the formula. In order this formula to work, I need to put an extra term here. I put the mu functional of omega g tau 1. Then you can check this. And this will give you V less or equal to 0. Using the same method, you obtain V less or equal to 0. But what does this mean? So this means mu, I put this as mu for simplicity. Mu will be bounded from below by tau m plus 1 minus t, 2 Laplacian f minus gradient f square plus r plus f minus m. Okay, so now it's good. Because around x0, you have a bounded geometry. You can move the time a little bit further. So you have all the high curvature derivative bound. You have u bounded from below. Okay, and what is f? U equals 4 pi tau to the negative 1. So f is also bounded. Okay, so u bounded from below here, and you can also see that u is bounded from above, because the local geometry is bounded. The integral of u is 1, so that means u is bounded from above, around the x0. Okay, u is bounded, so that means f is bounded. And the geometry, f satisfies some heat equation. So f's derivative and Laplacian, all high derivatives are bounded. So that you will obtain that this Laplacian f and gradient f all bounded. So put this information to here, you obtain there is a negative c coming from below. So that means this mu function is bounded from below. Now the mu function is just located in this domain omega. Then we can use the local collapsing proof of Perman. Mu function is bounded from below, and this tau n can be from 0 to r squared. Then you obtain a non-collapsing here. So the non-collapsing must hold here. So in this way, so we remove the space-time condition of Perman by a time slice condition scalar bounded from above. So we show this kappa non-collapsing estimate. So this is a localization. So this is by localization of Perman's functional and generalized using the local collapsing theorem. So that's the basic idea. But that's a rough idea. So what's the technical difficulty? So as I explained here, I need to show this formal. This is very formal. In order to make this analytically rigorous, we need a heat corner estimate. I need a lot of estimate. For example, I use the estimate which is inspired by the work of Professor Tan and Cho and Chen Jieyu. They use this heat kernel estimate around the boundary. So there are some regularity issue around the boundary of omega. You need to use the heat kernel estimate around there. So that makes this formal argument rigorous. So like Perman's original argument for V equals to 0, he just stated this is true. There is no analytical estimate. But in order to make that rigorous, we need a rigorous heat kernel estimate around the boundary of omega. Okay, so I stop here. As a kappa non-collapsing, so you know that so that you can construct an identity map from M aware from B to this. This identity map will be the Gromov-Host approximation. Yeah.
Our status prepare some local groups like Thai for so just too much in the first round. Okay, so anything, each one can have a beat. So.